we talk about the brain, we can't talk about the brain without talking about glial cells. I want you to know that there are 5 major types of glia. So if I ask you on a test, how many major types of glia are there? You're going to tell me 5. I also want you to know where they're located. And it's real easy, okay? Because 4 out of the 5 are located in the central nervous system. There's only 1 that's located in the peripheral, and that's the Schwann cells. Schwann cells. I'll get there in a second. Okay. So there's 4 glia, types of glia that are in the central nervous system, and 1 is in the peripheral, and that's Schwann cells. So the first glia we're going to talk about is astrocytes. Where is it found? CNS. Yep, you got it. CNS, central nervous system. I want you to know that they're star-shaped, and they are the largest and most numerous types of glia. Their cell extensions connect to both neurons and capillaries. And I want you to know the function of astrocytes. They transfer nutrients from the blood to the neurons. Our brain is made up of billions of neurons, so you have an idea of how important these astrocytes are. So oddly enough, when a patient has brain cancer, it's a little misleading because really the cancer is affecting the astrocytes. And that's with all cancer. It's usually involving the glia, okay? So there's one of the most deadly types of brain cancer is glioblastoma multiforme. It's what Ted Kennedy died from, John McCain, and it involves these astrocytes. So, and you can see how devastating it is because the astrocytes are the largest and most numerous types of glia. Very, very difficult to treat. How do we treat brain cancer? You know, when it's operable, we try to remove all that we can, right, of the malignancy, and then we do chemo and radiation. Chemo, though, doesn't cross the blood-brain barrier, so it's really not that effective, at least as of right now. And this is what it's talking about here. I'm not going to test you on the blood-brain barrier. I just want you to know, if we didn't have this blood-brain barrier, we wouldn't exist. Because it's exactly what it says it is, blood-brain barrier. It's going to protect the brain from anything toxic getting in. And that's very, very important. However, when the brain's damaged, like with brain cancer, that's when this blood-brain barrier becomes a problem because chemo won't go through it. So what we use instead is essential oils because they will cross the blood-brain barrier. It's not a cure, but and I've seen this with my patients, it will improve their quality of life greatly. I can't stress that enough. Things like frankincense, peppermint, it's amazing. We even use it, we've had some success with Alzheimer's. And like I said, not a cure, but it does improve the quality of life. So this is what the astrocytes look like. Remember, they're star-shaped. And then we have our second glia is microglia. And microglia, I'm gonna come back to slide 18 in a minute, but microglia is small, usually stationary cells. We see microglia in inflamed brain tissue, like in a concussion or something of that nature. They're going to come in, they get really big, and they're going to carry out phagocytosis. And what's phagocytosis? Yeah, so it's gonna eat any thing that is not needed. It too is found in the central nervous system. Epidermal cells are found in the central nervous system. Do you remember when we dissected the brain last semester? And I told you that the brain has 4 ventricles, right? Has the lateral ventricle, which is ventricles 1 and 2, has the 3rd ventricle and the 4th ventricle. Well, inside those 4 ventricles is where we're going to find these epidermal cells. And those epidermal cells are responsible for the secretion of cerebrospinal fluid. Okay? So some of the epidermal cells will actually secrete the cerebrospinal fluid, and others will direct the cerebrospinal fluid to where it should go. So very, very important cells. Okay, don't have to worry about 21. The next type of glia is oligodendrocytes. They are also found in the central nervous system. They hold nerve fibers together, and they help produce the myelin sheath. I want you to highlight that. I want you to always associate oligodendrocytes with the myelin sheath, and we're going to talk about the myelin sheath in a minute. The last glia is Schwann cell. Okay, and that's the only one that's found in the peripheral. And I want you to know that Schwann cells support nerve fibers and form the myelin sheath. So oligodendrocytes and Schwann cells are very important when we're talking about the myelin sheath.
Can you go back to Schwann?
I sure can. You bet. Okay. Slide 23. I want you to know the function of the myelin sheath. It permits rapid conduction in nerve fibers. It permits rapid conduction in nerve fibers. I also want you to know that the myelin sheath is formed by layers of Schwann cell membrane containing the white fatty substance myelin. Now think about the function of the myelin sheath. Okay, it said it permits rapid conduction in nerve fibers. What do you think, and it's found, the Schwann cells are found in the peripheral nervous system. So if this myelin sheath is compromised, how do you think it would affect our patients?
I know.
You got it, MS, multiple sclerosis. So let's go back and look at the picture that I skipped, because I want you to see this. This is the myelin sheath. Okay, as you can see, it surrounds every single nerve fiber. Okay, this is just a picture, an image of one nerve fiber. It surrounds all the nerve fibers. So if you have a new patient and they haven't been diagnosed with anything yet, but they come into the doctor because they're concerned, what brought them there? If they have MS but they don't know it yet, what would bring them to the doctor, do you think? What would their signs and symptoms be?
Their atrophy movements.
Well, yeah, weakness, fatigue, when they're walking, they may, be walking kind of like they're drunk. They're gonna fall, they can fall for no reason. That's what's going to bring them in initially, okay? As the disease progresses and this myelin sheath becomes more and more compromised, and you're thinking about the peripheral nervous system, what's going to happen to them eventually? Are they gonna be able to walk? No, they're usually confined to a wheelchair, and it gets to the point where they can't even blink. Okay, that's how bad MS can get. The only good news about MS is that sometimes it's slow. The progression is super, super slow, and the patient will respond to the medication. Sometimes a change of diet can help, but it can be a very, very devastating disorder. It affects their eyesight. They can, but they're doing something new now to treat MS. They're using stem cells, and they inject them nasally into the patient, and you do it once a year. And I had a patient that was, when she was diagnosed, she was 39, I think, 39 or 38. And she was going blind, she couldn't drive anymore. And she went and had this stem cells injected nasally, and that night her eyesight improved. And she's back driving. I mean, it's amazing. She's still a little off balance at times, but it's truly amazing. But insurance won't pay for it, and it's $10,000 an injection once a year. But we're going to talk more about MS. You're going to see MS on NCLEX. I want you to know it really well. But always associate MS with this myelin sheath. Satellite cells. Remember we talked about satellite cells last semester? When are they activated? When we're weightlifting or we have a injury. Okay. So I want to add to that a little bit, and I want you to know that satellite cells are actually Schwann cells that cover and support cell bodies in the peripheral nervous system. Okay, if you can remember that, I'll be thrilled. Okay, you're just going to add to what you already know about satellite cells, that they are actually Schwann cells. Okay, let's talk about the components of a neuron. Components of a neuron. So we have ribosomes, rough endoplasmic reticulum, ER, Golgi apparatus. Remember when we talked last semester about the cell, and we talked about all the organelles, okay? Nerve cells are no different. They have all the organelles. Neurotransmitters are packaged into vesicles. It provides proteins for maintaining and regenerating nerve fibers. I want you to know that neurons are excitable cells that initiate and conduct impulses that make possible all nervous system functions. And in order for them to work properly, they have to have proteins. So the ribosomes are gonna provide the protein, and these protein molecules are actually called neurotransmitters. And they're needed for transmission of nerve signals from one neuron to the other. Mitochondria is going to provide the energy for the neurons. So we can't talk about neurons without talking about dendrites. Each neuron has one or more dendrites, which branch from the cell body. The distal ends of the dendrites of sensory neurons are receptors, and we'll talk about that in a second. Dendrites conduct nerve signals to the cell body of the neuron. I want you to know that another name for cell body is soma. Okay, another name for cell body is soma, S-O-M-A. I want you to know that dendrites receive stimuli and conduct electrical signals toward the cell body and axon of the neuron. I want you to know that an axon is a single process extending from the axon hillock, sometimes covered by a fatty layer called a myelin sheath. And here's a really nice visual of the myelin sheath, and then we have the nodes of Ranvier, which we'll talk about in a minute. Do you remember the cytoskeleton from last semester? What did that consist of, the cytoskeleton?
The microtubule?
Yeah, the microtubules, right, the microfilaments, and what's its claim to fame? We even see the cytoskeleton in blood cells. And what's it do for the cell? It's the framework. It's the framework of the cell. So they have microtubules, microfilaments. It's going to allow the rapid transport of small organelles. Remember, we saw how the microtubule slides, it moves, and it's going to allow for that rapid transport of organelles. Slide 34, I want you to know really well. It's the functional regions of the neuron. The functional regions of the neuron. Really, it tells you what's happening in each zone just by the name alone. Input zone, without even looking, what do you think they're talking about? Input zone. What do you think is happening in that zone?
Incoming.
Incoming, it's receiving information, right? Input zone. What about the summation zone? What do you think there?
Thinking.
It's summing the information up, right? Okay. Conduction zone, it's going to, produce or, conduct. Output zone is going to be what it did. What was the result? So for input zone, you want to think of dendrites in the cell body because they are going to receive that stimuli. They're going to receive the information. The summation zone is the axon hillock. So in the axon hillock, it takes that information and it decides whether or not to send it further down the axon. It may just say, you know what, we don't need to respond to this, so it just stays there. That stimuli, it won't go any further down the axon. But if the axon hillock determines, yeah, you know, it needs to be sent further down so we can have a response, then that's what's going to happen. Okay, so the axon hillock, it's gonna sum everything up and determine whether or not to send that signal further down the axon. The conduction zone is where that information is going to, we're actually going to have a response. Okay, conduction zone. The output zone is what that response was. What did it do? So you want it on 35, you want to know this verbiage. The dendrites and cell body act primarily as the input zone, receiving nerve stimulation and initiating nerve impulses in response. The axon hillock is going to sum up all that information, it adds it all together, and it's going to determine whether or not it's going to be sent any further down the neuron. The axon is the conduction zone because its primary job is to conduct the nerve impulses from the axon hillock all the way to the end of the neuron. And the teledendria of the axon, along with the synaptic knobs, together act as the output zone, where vesicles of neurotransmitters are released for possible reception by a nearby neuron or effector cell. What determines if a neurotransmitter is excitatory or inhibitory? Let's just talk about acetylcholine, okay, because you know a little bit about acetylcholine. Acetylcholine is acetylcholine, okay? The neurotransmitter itself does not change. What makes it inhibitory or excitatory? It's the receptor that it binds to. Okay, it's the receptor that it binds to. So if we go all the way back, I want to make sure you get the big picture here. In the sympathetic nervous system, if the neurotransmitter acetylcholine is secreted in the sympathetic division for the digestive system, is it going to be inhibitory or excitatory?
It's gonna increase digestion.
Now we're in sympathetic. So we have a decrease digestive functions of the stomach, pancreas, and intestines. It's going to be inhibitory, okay? So that means that in this situation, acetylcholine has to bind with a receptor that will make it inhibitory. Does that make sense? And then we come over here to parasympathetic, we're talking about the same neurotransmitter, acetylcholine. But what's the difference? We have an increase in digestion, so acetylcholine in this case is going to be excitatory, right? Because the digestion is working, okay? And it all has to do with what receptor it binds to. Okay, go ahead and put that in your notes now, and I will elaborate on it more as we move forward. Okay, all neurotransmitters The receptors that they bind to will determine whether they're excitatory or inhibitory. This is really important for you to know moving forward.
Can you repeat that one more time? I'm sorry.
Sure. So, all neurotransmitters the receptor will determine whether they are inhibitory or excitatory. The receptors that they bind to will determine whether they're excitatory or inhibitory. On slide 36 is an excellent visual, if you guys are visual, of what I just said. You could study this picture, either up at the top, input zone, what are the structures involved? Dendrite, cell body, or soma. Okay. What's gonna happen here? You're gonna receive that information. That information is going to be sent to the summation zone. The axon hillock is going to determine whether to send it further down the axon. If it does, then we have the conduction zone, because that signal is traveling down that axon. And the last one, you want to think of the synaptic knobs that are on the ends of these dendrites. That's the output zone. That's where we're going to have the response. Any questions on that, guys? It's okay if you're not 100% on this right now, because we're going to do it again. We're going to go back to it. But if you just have that general concept of what I just said, you'll be fine moving forward. Okay. When we get to chapter 16, I'm going to go into even more detail. Okay, functional classification of neurons. We've already talked about afferent and efferent, right? There's one more, though, that I want you to know. It's called interneurons. Interneurons. I want you to know that interneurons are only found in the central nervous system. Interneurons are only found in the central nervous system. Just to reiterate, afferent neurons conduct impulses to the brain spinal cord. Efferent neurons conduct impulses away from the brain and spinal cord. What's another name for efferent?
Exit.
Exit or motor. And what about afferent? Sensory, you got it. Just remember, I could say sensory neurons here. It's the same thing. I don't want you to get confused. On the test, if it says sensory neurons, think afferent. If it says motor neurons, think efferent. Okay. All right. This, my nurses, is a 3-neuron reflex arc. A 3-neuron reflex arc. Why 3? Well, because we have the afferent neuron, we have the efferent neuron, and we have the interneuron. So it's called a 3-neuron reflex arc. This 3-neuron reflex arc is the most common we have in our bodies. So let's look at how it works. We have our finger, right? The receptor is going to be the finger. The stimulus is going to be the tag. Okay? So if you take something sharp, which I don't have, we'll pretend this is sharp, okay, and it's touching my finger, okay? What's the first thing that's going to happen? Yeah, but you would not believe what has to happen before we pull our hand away. Let me show you. So here, we have the afferent neuron that's going to be activated, and it's going to send a signal to the interneuron. Where's the interneuron located? Central nervous system, yes. And that interneuron is going to send that information to the motor neuron or efferent neuron, and then once we receive that information, we're able to pull our hand away.
So is that why some people, when they touch a hot stove, they don't have the pain receptors?
That's exactly right. That's it. Yeah, they're missing that. So, you know, if this was a hot stove and I put my hand here and I can't feel pain, hopefully somebody will tell me to move my hand, right?
So it's just,
Now, here's something though that your book, I don't like the way your book shows this. It makes you think that the brain is not involved at all. But it is. It's just that because of this interneuron, we have already removed our hand from the sharp object before the brain has a chance to tell us, because of this interneuron. But the brain is definitely involved, okay? It's just that it happens so quickly. Does that make sense? Okay, I really want you to know this. So 3 neuron reflex arc, it's the most common we have in the body. Anytime that we have a reaction, like, you know, a hot stove, or we touch something that's really, really cold and we jerk our hand away, we're using this 3 neuron reflex arc. Now, we only have one other, and it's called a 2 neuron reflex arc. And the 2 neuron reflex arc only uses the afferent neuron and the efferent neuron. It doesn't use the interneuron. And the only one that I can think of, to give you a good example, is the patella reflex, that knee-jerk reflex. You know, when you're a kid and they do an exam and they hit that only uses the 2 neurons.
when the reflex doesn't go anywhere on the knee, why do they have to put it on like this?
To see if you're able to do this, because if you weren't able to do this, then right away they're thinking maybe there's a neurological issue going on. Some people don't have the knee-jerk reflex. When we get really worried is if at one point you did have it. So like, let's say all growing up you had it, and then now you're in your 30s and you don't have it. Well, they may send you for additional testing because it could be something more serious, or it could be absolutely nothing. But that's one of the things they want to make sure that you're able to, and they may do a number of tests while you're at the general practitioner's office just to see if it's something that they feel should be sent to a neurologist. And some doctors may still send you there. You know, it just depends. We're going to talk more about, there's the Babinski reflex. When a baby's born, one of the first things they do is they touch the sole of the feet to see if they have a Babinski reflex. And we want to see that. We want to see that Babinski reflex up until the age of 2 years old. Now, if you have a patient that comes in and let's say they're 25, and they have a positive Babinski reflex, then right away we're thinking the worst case scenario. It could be meningitis, it could be a stroke, but it's very, very serious. It's never something minor. I mean, it's really serious. what?
Don't fix my feet.
Yeah, I know, right? So this is the 3 neurons, we've already talked about it. If I ask you on the test, what does a 3 neuron reflex arc consist of? You're gonna tell me afferent neuron, interneuron, efferent neuron. Okay, and again, you already know it's the most common. I just want you to know the definition of this right now. We're gonna talk more about this when we talk about strokes. But ipsilateral reflex, I want you to know that the response is on the same side of the body as the stimulus. Okay, ipsilateral. Contralateral is on the opposite side of the body as the stimulus. Please know this.
So when you see that, it being on the opposite side. So like if you would do stimulus on one side and you'd feel it on
You
the
would,
other.
you would see the response on the opposite side.
Is that like kind of like when my cousin had a stroke, they have to constantly start feeling his face and arm?
Yeah, because with a stroke, let's say, he suffered a stroke on the left side of the brain, it's going to affect the right side of the body. So that's why I want you to know this, but we'll go into more detail, later regarding strokes.
My mother-in-law had a stroke first semester at the concert I went to. She had a left-sided stroke. She still has no given back in the right side of her arm everywhere, but just the arm still.
And she's okay.
Yeah.
The worst strokes possible are when they affect the brainstem. They usually never recover 100%, and in most cases, they don't survive. It's very, very serious. If you guys are interested, there's a great video, documentary. It's about a bodybuilder that had a brainstem stroke. He, was here in the States, of course, and he had, his insurance ran out after 12 months. And he was doing rehab, and of course, they just dropped him. And he went to China, and he did acupuncture, and I think it's called 9,000 needles. It's either 9,000 or 10,000, but after 24 hours there, the improvement was unbelievable with acupuncture, and they did some other things. But it's a great documentary if you're interested. You can watch it on, I think YouTube, or it's really, really good. Okay, and the 2 neuron, we already talked about that. I do want you to know an example of a 2 neuron reflex arc is the knee jerk reflex. I want you to know that we have 2 types of synapses. We have electrical and chemical. And of course, a synapse is where nerve signals are transmitted from one neuron to another. So electrical is what we see with babies and young children. Their synapses are almost entirely just electrical. And then as they grow and they start to become adults, then the chemical synapses take over. Okay, and what do I mean by chemical synapses? Those neurotransmitters. I want you to know the repair of nerve fibers. Once nerves are damaged, like with neuropathy, it's very, very difficult for them to repair themselves, okay? In order for a nerve fiber to repair itself, the damage is not too extensive. The cell body and the neurolema remain intact, and scarring has not occurred. If that's the case, then those nerve fibers can be repaired. Okay?
Is there any way to see that, or is it just hope, like with patients?
When, hope, especially with the scarring, you know, because we don't know. I mean, but that's why if anyone suffers a spinal cord injury, and let's say that the neurologist, you know, he's looking at it and he's like, okay, he's probably 99% sure that the patient's gonna be paralyzed from the neck down. They shouldn't say that right away, because we have to wait at least 24 hours for that swelling to go down, in most cases 72 hours. Because sometimes when the swelling goes down, it's not as bad as what it first looked like, okay? So after injury, the distal portion of the axon and myelin sheath degenerates, macrophages remove the debris, and the remaining neurolemma and endothelium form a tunnel from the point of the injury to the effector. At that point, new Schwann cells will grow in the tunnel to maintain a path for the regrowth of the axon. Like I said, you know, nerve is has the least amount of ability to repair. Very, very difficult once that nerve is damaged. Disorders of the nerve cell. We can have tumors in the central nervous system. We can have tumors in the peripheral nervous system. You are responsible, as always, for all the pathologies that we talk about. Most disorders involve glia, not neurons, as I said at the beginning. Glioblastoma multiforme is a highly malignant form of astrocytic tumor. It spreads throughout the white matter of the brain, so I want you to know that about glioblastoma multiforme. So it's very, very deadly. Patients, I think, when they're diagnosed, I think the average is about 15 months. Yeah, it's really tough. Adenoma is a glial tumor arising from those epidermal cells that are found where? Remember, they secrete cerebrospinal fluid, and they're found in the four ventricles of the brain. Excellent. The acoustic neuroma, acoustic, what do you think of? Sound or hearing. So acoustic neuroma is a lesion of the sheath of the Schwann cells surrounding the 8th cranial nerve. There's one of your cranial nerves, and it's called vestibulocochlear, but we'll get to that. And it's responsible for hearing and balance. So that gives you the 8th cranial nerve right there. What's the function? Hearing and balance. Neurofibromatosis is a group of genetic diseases often characterized by numerous fibrous neuromas and skin spots throughout the body, and this is what it looks like. This is a moderate case. I've seen where the whole body is covered with them. They have different stages, okay? This would probably be about stage 3. Okay. We can remove them, but they usually always go bad. Okay, my nurses. Lecture number 1 down. Yay!